In this lesson, we'll begin exploring how to calculate the energy involved in heat transfer. And it's the beginning of the math that you have to learn to do in order to be able to do the ice cream lab. All right, so what we're going to do is we're going to take, in the fall, I usually take Unit 10 out of order. So I teach Unit 10 second so that we'll be able to do the ice cream lab while there's still some warm weather. Okay, now just so you know, we're still a couple days away from being able to do that. We're going to start with the kind of math that you're going to have to be able to do in order to do the ice cream lab, and then we'll get into some other things. So even as far as Unit 10 is concerned, we're taking it somewhat out of order so that you can get started on it. What you have to be able to do to eat ice cream. Well, everybody's going to make ice cream because that's the lab. That's part of seeing how this concept of heat exchange works. So instead of doing a heat exchange lab in the lab, we go doing a heat exchange lab outside, and you make ice cream by doing heat exchange. And so we're going to take the time to learn first how to do the basic math. Okay, so first I've got to explain what the math is, all right? We need to know some basic concepts here. A lot of times students come to high school chemistry and they don't really understand the difference between temperature and heat. Okay, so let's be clear. Heat is a form of energy. Heat is a form of energy. Okay, we measure heat sometimes in calories, but in most chemistry classes we measure it in joules. Joules. Okay, heat is a form of energy. We measure it in joules. Temperature, on the other hand, is a relative comparison of the momentum of particles in a substance. It's a relative comparison of the momentum of particles in a substance. Okay? Temperature is a relative comparison of the amount of momentum of the particles in a substance. Now, if you don't remember about momentum from earlier science classes, let me tell you a little about momentum. Momentum is a combination of two things. They are directional travel and mass. Momentum is two different things sort of combined together: directional travel and mass. So we just happen to be teaching this class during football season, and if you have a really large running back, he can be traveling, let's just say he's traveling at 15 miles an hour. We don't use miles an hour because that's English measurements, but just for us right now, okay, we could say he's traveling at 30 kilometers an hour, okay? He's traveling at 30 kilometers an hour, and he's a really big guy, all right? Compare that to, say, a wide receiver who's not such a big guy, but he's also traveling at 30 kilometers an hour, okay? The running back, because he has a much larger mass, he's much bigger, has more momentum than the wide receiver does, even though they are both traveling at the same rate of speed. You with me? It's kind of the difference between running into a pickup truck and running into a train. They may be both traveling at 50 miles an hour, but which one's going to do the most damage? The train, because it's got more mass and therefore more momentum. You see that? So temperature is a relative comparison of those two things. Now, temperature is somewhat like heat in that it is a relative comparison of the amount of heat energy. The problem is temperature doesn't take into account everything that heat does, and vice versa, okay? Just got to know that heat is not quite the same thing as temperature. Temperature is not a measurement of energy. Heat is a measurement of, it is a type of energy. So when we measure the joules in something, we are measuring the amount of energy, okay? They are both both have a lot to do with the particle movement. All right, heat is the result of particle movement. Okay? All right. So there are some formulas that will help us figure out how much heat is. You cannot measure heat directly. That's something you probably need to write down. You cannot measure heat directly. All right? You cannot measure heat directly. What we have to know is what is the temperature change. And not just the temperature, but the temperature change to calculate the heat. We also have to know some other things too. So let's look at the basic equation and start to get a grasp of what's involved here. There's really two basic equations for calculating heat energy, or heat change, the heat exchange in a substance. And one has to do with what happens when the temperature is changing, and the other equation has to do with when you're changing physical state. Okay, so let me explain that a little bit. If I have a block of ice, just an ice cube maybe, and I may start out at negative 10 degrees C. All right, so it's below freezing. The freezing temperature of water. What is the freezing temperature of water? Oh no, y'all are using Fahrenheit. Not Fahrenheit. We don't use Fahrenheit. Oh my, it's 0 degrees C. Yeah, you can tell this video is being recorded in America because we're about one of the only countries in the world that still uses Fahrenheit. Okay? 0 degrees C is the freezing temperature and the melting temperature of water. Okay? It happens to be the same temperature. It melts and freezes at the same temperature. It's all about how much heat is being added or taken away. If you take energy away, heat energy away, at 0 degrees C, water freezes. If you add energy to water at 0 degrees C, it melts the water. Okay? And so you got to understand the difference between the temperature and the heat energy. Okay? So water can be at 0 degrees C, and its temperature doesn't change at all. But you're adding heat or taking away heat. And that's why one of the reasons why, that illustrates why they're two different things. All right, so we've got two different equations, one for when you're changing the physical state, like melting water or boiling water, and the other is when you're changing the temperature. So once you get the water melted and it starts out at 0 degrees C, all liquid water, then you can heat it up to 50 degrees C or whatever, okay? So what's the boiling temperature of water? Centigrade scale or Celsius scale. What is it?
Like what? Like 100 something?
Not 100 something, 100.
Oh yeah.
Okay? You need to know these. These are things you should know from memory. All right? Freezing temperature water, melting temperature water, 0 degrees C. Boiling temperature of water, condensation temperature of water, 100 degrees C. Okay? It's easier to remember than 32 and 100 and 212. Okay? If you're on the Fahrenheit scale, that's the freezing and boiling temperature. Okay? But we don't use the Fahrenheit scale in here. Okay? All right. So the equation that you use for calculating heat energy by temperature change, when you're changing the temperature, so we have to have a physical state that's not changing, we're just heating up water, or we're heating up something that's solid, or heating up something that's gas, okay? That basic equation is Q, and sometimes you see it written as a capital Q, but I like lowercase q, is equal to the mass of the object, or the substance, the material we're looking at, the amount of it, times something called CP, or specific heat, times change in temperature. Okay? So this is no change of state. That's Q. M for mass, specific heat. All right, so this is heat. Okay. This is mass. This is specific heat. And this is the change in temperature. What's the question? Why is it a triangle? Good question. The triangle is just a symbol that we use to mean change in something. Okay? So this is the Greek capital letter D. Okay? So it's delta T. Okay? Delta, that's the Greek letter delta, which is our letter D, which translates to our letter D. Okay? So this is the Greek letter delta, and a capital letter delta to a chemist and a physicist means change. Okay? So Q is heat, mass, specific heat, change in temperature. So specific heat is something you need to know about. Specific heat is unique for every substance and for all the physical states of that substance. Okay? It's unique for every substance and for all the physical states for that substance. Okay? And when I say physical state, can you tell me what that means?
You mean like gas, liquid, or solid?
There you go. Gas, liquid, or solid. Okay? So, water, for example, has 3 different specific heats. Has a specific heat for solid water or ice, has a specific heat for liquid water, and has a specific heat for steam. Okay, they're all different. So you have to know what the specific heat is. Most of the time we look it up. For pure substances, there are these really large collections of data. I have a couple of them in here that I could show you later, I guess, that you can look up what the specific heat for all these different individual substances are. Now, the things you won't find in those volumes are things that aren't substances. Substances to a chemist are either elements or compounds. The word substance to a chemist refers to an element or a compound, okay? When we say substance, we don't mean mixtures. And mixtures or solutions have their own unique specific heat, okay? If I'm using salt water, as you do when you're making ice cream, then the amount of salt affects the specific heat. Okay, so if you change the amount of salt, you're changing the amount of specific heat. All right, so you have to be aware, of what the specific heat is, or calculate what the specific heat is. Now, the specific heat of water is pretty well known, and so a lot of the time, most of the time perhaps, we use water as the comparison to calculate or determine what specific heat is. You are going to have a set of test references for looking up specific heat for water. Other than water, however, I'll have to give you the specific heat for whatever the substance is, all right? But there is a specific heat that you need to know about from memory. I mean, everybody should know the specific heat of pure water, liquid water, okay? Everybody should know the specific heat of liquid water. And the specific heat for water in liquid form is 4.18 joules per degree C per gram. That's an L for liquid. Okay. So now degree C is a unit of temperature, and while the Celsius or centigrade scales begin at a different place, the size of the degree for Celsius and Kelvin is the same. So sometimes you'll see Kelvin in the place of degree C.
Is that an 8.5?
What now?
Is that an 8.5?
That's an 8. 4.18 joules per degree C per gram, or 4.18 joules per Kelvin per gram. Okay? And except for water, you need to, you're going to have to, I'll have to give you the specific heat. But you'll have test reference looks something like this, and it has the specific heats right on the front of the test reference, okay? And you've got liquid water and gaseous water and solid water, and there are the specific heats right there. And you can see that the numeric value stays the same, and it can have either degrees C or Kelvin on the bottom. Okay? All right. Now, so if we want to know how much heat exchange there is, or heat change there is, we need to know the mass, and we can measure the mass. We've got balances for that. We can look up the specific heat, and we can determine the change in temperature. How would you determine the change in anything? How would you determine the change in something? Yeah, subtraction. Right? You have to have the beginning amount and the ending amount, and you subtract. Got it? Now, delta T, or change in temperature, is always calculated in this fashion. It's temperature final minus temperature initial. Okay? Final temperature minus initial temperature. And almost everything in chemistry is almost always final minus initial. Okay? Almost all of the change things that we calculate is always final minus initial. And just remember that. Final minus initial. Okay? Got it? All right. So if the temperature is going up, okay, you'll have the final temperature minus the initial temperature, you'll have a positive number. If the temperature is going down, the final temperature is lower than the initial temperature, so you're going to get a negative number. So the change in temperature's sign will tell you whether the temperature is going up or down. Make sense? All right. Now, if that's true, Cp is always a positive number. Mass is always a positive number. So the amount of heat exchange will either be increasing because the temperature is increasing, or decreasing because the temperature is decreasing. Okay? And that makes sense if you think about it. If you're putting heat energy into something, let's say you put a pot of water on the stove, you turn on the element, turn on the stove, turn the temperature up, the element on the stove heats up, it becomes red looking, and it transfers heat to the water. Well, you're transferring heat from that heating element on the stove into the water. So you're adding heat to the water. Does that make sense? So it makes sense that if the temperature goes up, that's an indication that the amount of heat contained goes up. That make sense? And if the temperature goes down, then you're removing heat energy. Okay? So if I take a cup of water and I put it in the freezer, it's going to remove heat energy from that cup of water, and eventually it will probably freeze. Or if you just put it in the refrigerator, it might just cool down. Okay? All right. So you need to know that change in temperature is always final minus initial, and this is the equation for change in temperature. Okay? So let's do a little quick math here, practice some things. What do you say? Okay. Now you have everything you need to solve this problem. Now, in the previous unit, we learned how to set things up using dimensional analysis. So you cancel units. All right? This will work exactly the same way. If you set up everything the way you've been taught to set it up, you should end up canceling all the units except the one you're looking for. And if we're looking for the amount of heat energy, what unit of measurement should we have at the end? Joules. If you set it up right, then all the units of measurement should cancel except joules. That make sense? All right, so let's see if you can do that. Set it up, work with a neighbor if you want to, all right, and discuss it, try to set it up. See if you can figure out how to set this up. Shouldn't be hard, okay? This is simple algebra.
Oh, okay.
All right, here's our equation,
Okay, so we are doing like that.
okay? We're looking for how much heat energy will be transferred. Well, there's the heat energy right there.
Yeah.
So I'm going to write down the equation. Look, guys, when you solve these problems, always write out the equation. All right? And then plug in the values, okay? Always write out the equation, then plug in the values. Okay? This is going to help you a lot with a lot of things we do in here. All right. So what is M? M is mass, and the mass in the problem is 3.50 grams. So I'm going to plug in 3.50 grams. Okay? And what is specific heat? Well, is water solid, liquid, or gas between 20 and 50 degrees C?
You know,
I want to say it's going to be a liquid.
Yeah, if it freezes at 0 and melts at 100, then it's got to be liquid between 0 and 100, right?
Yeah.
All right. So we have liquid water, and the specific heat, okay, for liquid water is this right here, okay? 4.18 joules per degree C per gram, okay? And then we need to have the change in temperature, which is this what we put here on the end, change in temperature. Well, how much did the temperature change then?
30 degrees Celsius.
30 degrees Celsius. Is that a positive number or a negative number?
Uh,
Let's make sure. Here's delta T, and we want temperature final minus temperature initial, okay? And the temperature final is
30.
50 degrees C is the final temperature.
My bad.
That's what we're going to. We're heating from 20 to 50. Isn't that the final temperature?
Yeah.
Okay? And we're going to subtract the initial temperature. The beginning temperature is 20 degrees C. Okay, so therefore, delta T
Positive.
is equal to a positive number of 30.0 degrees C, right? All right, so we're going to put that in here now. 30.0 degrees C. All right?
Yes, sir.
We just plug in the values. This is plug and chug chemistry. Okay? Plug and chug. Now remember, we're using dimensional analysis, right? So we should be able to cancel all the units of measurement except the one we're looking for. So let's put this over 1. Did I change how much this value is by putting it over 1? No. 3.50 grams is the same as 3.50 grams over 1, because dividing by 1 just gives you the same answer. I'll put this one over 1. This is just to make it convenient to figure out how to cancel things, okay? So now what units of measurement can I cancel? Celsius and grams. Okay, degrees Celsius and grams. Guess what I'm left with?
Joules.
Bingo. That's what we want to do, isn't it? So all we have to do now is to multiply what's across the top, because there's really only ones across the bottom. And the way that I taught you to do this is you're going to, when you have a math problem like this, everything across the top gets multiplied. You divide by what's on the bottom. Well, there are no numbers except for 1 on the bottom, so dividing by 1 just gives you what you started with. All we have to do is multiply by what's on the top here, okay? So 3.50, went off the screen, 3.50 times 4.18 times 30.0, enter, and we get 438.9, and the only units left are joules. Okay. How many significant digits do we need in our final answer?
3.
I got 3 here, and 3 here, and 3 here. That's the least digits. We should have 3 digits as the final answer. And so we'll have 439 joules. Okay? So pretty straightforward math. It's not real complex, all right? Don't make this hard when it doesn't have to be. Okay? All right? Okay. Let's practice another one. I'm going to give you another one. You get this one? All right. Yeah, it's got to be in scientific notation. Very good. Somebody pat that young man on the back there. All right. How many significant digits do we need? 3. 1, 2, 3. 1, 2, 3. This has 4. You want the least digits. 1, 2, 3. Underline all that. Draw an arrow. Now, decimal places have to be moved. They've got to move this 1, 2, 3, 4 places to make it scientific notation. So it's got to be right there between the 1 and the 2, just to the right of the first non-zero digit. And so now we're going to get a negative 1.2, and this 6 makes the 8 round up to a 9. 1.29 times 10. We moved it 1, 2, 3, 4 places times 10 to the 4th joules.
Wait, doesn't have to be
Okay, so here's a new problem. If 24.32 grams of steam is heated from the boiling point to 135 degrees C, how much of the heat energy in the steam sample change? Okay, I gave you the specific heat of steam. Okay, so solve the problem. Okay, so the equation, if we have, now listen, first we need to evaluate the question to make sure we're using the right equation, okay? Because in a little bit, we're going to have more than one equation, all right? This equation, we say we're heating steam from the boiling point to 135 degrees C. So it says it's heating it, all right? So we're not changing the physical state, we're only changing the temperature. Well, I shouldn't say only, we're changing the temperature, okay? So if we're just changing the temperature, then this is the equation we want here. All right, Q equals mass times specific heat times change in temperature. Okay, so I'm going to write that down. Q equals mass times specific heat times the change in temperature. Okay, the mass is 24.32 grams. Okay, the specific heat, now this is steam. This is not the same specific heat as liquid water. It's this specific heat right here. I gave it to you, so it should make it easy for you here. And then we need to have the change in temperature. All right, the change in temperature is always temperature final minus temperature initial, okay? Ending temperature minus beginning temperature, okay? Final temperature is 135 degrees minus the boiling temperature, and the boiling temperature of water we said is 100 degrees C, which means we have a change in temperature of 35 degrees C positive, right? Okay, so we're going to put 35 degrees C here. Put these two numbers here over 1 because it just makes it easier to see how to cancel things out. Canceling out grams, canceling out degrees C, left with just joules, and joules measures energy. That's what we want to be able to do. Go to the calculator, and we'll go take 24.32 times 2.05 times 35. Okay? And we get this great big number, 1,744.96 joules. Okay? But we need to round this to how many digits?
Two.
2 digits.
Yeah.
Yeah, there's 2 digits here. 2 significant digits. Everything else gets rounded off because we have to move the decimal place over here. Then we need to have this answer in scientific notation. 1, 2, 3 places to the left. 1.7 times 10 to the third joules. Okay? Okay, here's the question I just got. Why not write 35.0? And here's why. When you're adding and subtracting, you always put your numbers vertical, right?
Yeah.
And so we said 135 degrees C, which is our final temperature, minus the initial temperature of 100 degrees C. Now that 100 degrees C, you could put reasonably put a decimal place and some zeros after it because it is known to be. That's how the Celsius scale is set up, so that the boiling temperature is 100 degrees C. So that's an absolute number, but this one's not. In the problem, we only gave you 3 significant digits. So no matter how many zeros we put afterwards, there would be empty slots here. We still round it off to 2 digits. That makes sense? And so that we have only 35 degrees C. We can't put extra zeros there because that would be lying about precision.
I'm just saying, like when we had it, like in the last problem, it was like 80.0.
Well, in that case, I gave you 80.0 or measurements to 1/10 of a degree C. So you had to have an answer that reflected that degree of precision. Okay? All right, now, here's the new equation you need to know. In the case where we have a change of state, all right, so this is not a change of temperature problem, it's a change of state problem, okay? We have a different equation. Since there's no change in temperature, we can't use that delta T term because that's change in temperature. When we're changing physical states, the temperature doesn't change, okay? When you're changing physical state, the temperature doesn't change. Now, I'll show you a graph on that later, probably tomorrow or something, but right now, just take my word for it. When you're changing physical state, the temperature doesn't change, okay? So, since we don't have a change in temperature, we can't use delta T. So, for change of state, so this is going from solid to liquid, or liquid to solid, or from liquid to gas, or gas to liquid, And technically, you can also go sometimes directly between solid and gas.
Yeah.
That's a process called,
I forget the name, but it's like,
okay, the process is called sublimation.
yeah, something.
When you go from solid to gas without going to the liquid state, it's a process called sublimation. Dry ice, in atmospheric conditions on the planet Earth, dry ice does not go through the liquid state. You go straight from solid to gas.
Isn't there some kind of purple thing that comes out too?
Oh yeah, you're talking about iodine.
Yeah.
So iodine is purple when it's a solid, and it goes directly between solid to gas. It doesn't go to the liquid state. Now, if you put it under both iodine and carbon dioxide under enough pressure, you can get liquid CO2 or liquid iodine. Okay. All right. Now, that's not to say, don't confuse the iodine, supposedly iodine, quote unquote, that you buy in the drugstore to put on cuts and things like that. That's actually a solution of an iodine ion. It's not actually pure iodine, so don't be confused with that. But anyway, so change of physical state. The equation doesn't include a delta T. It still has exchange of heat. So you're putting heat into something to melt it or boil it. You're taking heat out of something to condense it from the gas state to the liquid state, or taking heat out of it to change it from a liquid state to a solid state. If we're going through the sublimation process, you put heat into it to change it from solid to gas, and you take heat out of it to change it from gas down to a solid. That's called deposition. Anyway, the equation here that we want is you still have mass. We're simply going to multiply that times something called the change in enthalpy, delta H. Okay, so H is a term that we call enthalpy. Enthalpy. Okay. Now, you can determine enthalpy through things you can do in the lab, but for the most part, we tend to look that up most of the time. There's a lot of enthalpy values already listed for you. Okay. But you have to know which change of state you're going through. Okay. For water, if we're going from solid to liquid, or from liquid to solid, so we're going either way. Okay, that's called the heat of fusion. All right, let's call that heat. Let's write that down as heat of fusion or enthalpy of fusion.
What is that word next to
Enthalpy.
Okay, the value there is 334 joules per gram. Okay? If we're going from liquid to gas or back, and this is often called the heat of vaporization. That is 2,260 joules per gram. Okay? So this is a huge number by comparison to the other values you've been looking at for the specific heat and for heat of fusion. This is huge. Okay? And this is kind of an aside, so we're taking a little detour here for a minute. When you get burned by steam, you're not actually getting burned by the steam itself so much. Okay, you're getting burned most of the time because of the heat of vaporization. So as the steam hits your hand, and the surface of your hand is less than 100 degrees C, that steam then condenses from gas water to liquid water, and it takes this heat energy and transfers it to your hand. Okay? So most of the time, the worst part of a steam burn is when the steam is turning from a gas into a liquid, because it's taking that heat energy that it contains and transferring it to your hand. And that's why it's such a bad thing to get burned with steam, because it has such a huge heat of vaporization. Okay? And that's people are usually kind of blown away by that. You know, you're not being burned by the heat of the steam. You are, but you're mostly one of the worst things is the heat of vaporization when it changes from gaseous state to liquid state because its heat of vaporization is so high. Okay? All right. So this is our equation, and these are the two values. So this right here, this is the change in enthalpy of fusion, which means we're going from either solid to liquid or liquid to solid. Okay? And this is the change in enthalpy for vaporization for water. Okay? So here's a practice problem. Hey. Okay. The heat energy involved here is the heat energy to completely change the entire sample from liquid to gas. You got that? And that's important. If we were only changing half of it from liquid to gas, the math would be a lot more complex. So right now we're sticking with something that's a bit simpler, okay, to change all of it into gas. So all you got to do, this is plug and chug. Plug in the mass, plug in the enthalpy value here, okay, and you can find it which one is the one you need right here, and do the math. Pretty simple. Okay? So solve that problem again. You can work with a neighbor. All right. This is an even simpler calculation than the last problem. Okay? Look, we are changing. You've got to evaluate the problem, interpret what it's saying, and all we're doing is we're changing it into steam. The temperature is already up to 100 degrees, all right? So it's at the boiling temperature, but it hasn't boiled away initially, or hasn't boiled at all initially. And it's saying how much energy is going to be used up or added to the water to change it all into steam. Okay, that's what the question is. Well, for that, then, we're only using this equation, Q equals mass times the change in enthalpy for this physical state change, and this physical state change is, I'm sorry, not V, but I mean not F, but V. Okay, this is vaporization. Okay, so the mass is 12.75 grams. The change in enthalpy for vaporization is 2,260 joules per gram. Okay, put this over 1, cancel out grams, and do the math. Multiply, yeah. Pretty straightforward, pretty simple, really. And so we're going to have 12.75 on the top times 2,260. And we get this big number, 28,815, and the units we have left are joules. Okay? Now, we look at these numbers here, and I can see that I've got 4 significant digits here, and I've got a number here where the last digit is not clearly going to be significant, right? This really should be 3 significant digits, okay? Maybe I should be writing this 2.26 times 10 to the third power, all right? But that's just the way it's just simpler, okay, to do it that way for right now, all right? But you need to know that really should be 3 significant digits. So we're going to underline everything but the first 3 digits, 1, 2, 3. And since I'm getting rid of a number or digit rather in the ones place, by rule, this answer has to be written in scientific notation. The rule is that anytime you have to round off a number in the ones place, you've got to change the answer to scientific notation. So move the decimal place that's implied here from here to 1, 2, 3, 4 for it to be in scientific notation. The decimal place has to be just to the right of the first non-zero digit. And so we're going to round it off to 2.88 times 10 to the 1, 2, 3, 4, fourth power joules.
But I thought it was 4.
It's only 3 because while this number does have a 0 here, that 0 is not shown to be significant because there's no decimal place here to show it. The 0 matters because it's kind of a placekeeper of sorts. It indicates what your order of magnitude is. If I were just writing 226, 226 is an order of magnitude smaller than 2,260. Okay? All right, any questions about that? Yes?
Why are you writing this time?
Because this number that we first came up with in the calculator has 5 significant digits, right? But we can only have 3 significant digits because of our measured and calculated numbers. This one has the least digits, it only has 3. So our final answer has to be in 3 digits. Anytime we're rounding off a number in the ones place, like this, we must, by rule, write the answer in scientific notation.
So what if it was like a 1 1 at
Yeah, then over here, well, you still would have to write it in scientific notation because when you round it off to 3 digits, the 1 and the 5 have to go away. If we're getting rid of a number in the ones place, like this 5 here, we're getting rid of it, then we have to write the answer in scientific notation. When would you not write it in scientific notation? If you're not rounding off a digit in the ones place.
It was just 226.
What now?
It was just 226.
If the final answer was 226, then there would be no reason to write it in scientific notation. You're right. Huh?
Like 260 joules, right there. That's wrong right there? Yeah. If there wasn't a 0, you said it before.
Oh, if there was a 1 there, then that would have 4 digits. And then we want our answer in 4 significant digits instead of 3. But we still write it in scientific notation because we still have to get rid of the 5 in the ones place. Okay. The rule is this. It's very simple. Listen carefully. If you have to round a digit in the ones place, then by rule, you must write your answer in scientific notation. Okay? The question that was asked a moment ago is, if this number were actually 2,261, would that change any of this? And it would. If this number were 2,261, well, there would be no 0 to cause any confusion. It would mean that this number had 4 significant digits. As it is, this 0, we don't know if it's significant or not. We have to assume it's not. We assume this number then has 3 significant digits. But if it has 4 significant digits, with a 1 there instead of the 0, this number here also has 4 significant digits. That means our final answer would have to have 4. We still would have to round off the 5 because 4 digits would stop at the 1. Okay? So we'd write 2.88, this 5 would round this 1 up to a 2, 2.882 times 10 to the 4th joules. Okay? All right. So, look, this math here is simply plug and chug. Okay? That's all it is. Now, heads up. This equation right here is the one we use when we're changing physical states. All right? The previous equation we're looking at today is what we use when we're changing the temperature. All right? So we're not changing physical state, just the temperature. If you're doing both, listen carefully. If you're doing both, that is to say you are going where you're both changing the temperature and changing physical state, then you calculate the two of them separately and add the two answers together. Okay, it's simple. You just add the two answers together. All right? What we're going to find out about your ice cream lab is that we're taking these two equations here and we're saying that one substance is changing state and the other is changing temperature, and we're exchanging heat between one and the other. And we'll figure out what happens with that. We don't do that today, but that's what the ice cream lab is about. And the math you have to do just takes these two equations and figures out the heat exchange and whether you have enough capacity to freeze the ice cream or not. That's all it's about. But for tonight, we're doing a combination question where you have to figure out how much heat is exchanged as you heat it up, then separately calculate how much heat is exchanged as you change the physical state, and add the two heat energies together. Okay? That's what we're doing tonight. When you read this problem, that's what it's telling you. We're heating it up from 45 degrees C to boiling, and then boiling it all into steam. So you're doing two separate equations, right? You need to do your homework always on a separate sheet of paper.